And now we'll turn it over to NERSC, to Helen He, to start us off with OpenMP. Helen, are you ready?
Yes, I'm here. So Oscar and myself are presenting the OpenMP talk today. We would like to thank Tim Madison, Barbara Chapman, Michael Clam, who allowed us to use some of their presentation and slide materials for this talk. So, before this event, I think organizers did a good survey about what's the basic knowledge that the attendees have. So more than half of people are new to OpenMP or only know the basics. So the goal is to introduce, starting from the background information, and have some of the several advanced features and tips also included. And then also Oscar's going to talk about GPU and vectorization, also plus what's new in OpenMP 5. That's the basic agenda. Next slide, please. I'm going to cover background, how to create parallel threads, and work with work sharing, especially with loops, the data environment in OpenMP, tasking, and thread affinity. So about an hour-ish. So we have less than 2 hours total. With this short time, we prepared exercises, but we won't have time to do it during the presentation. So please do it after. And the introductions will read me with lots of details to follow what to do. Next slide, please. Today's HPC computers have increased core node counts, large number of node counts, plus within each core, there are large number of node counts, and then within each node, there are lot more core counts, with increased vector lengths. So, and also there are accelerators. So for threading, for vectorization, and working with accelerators, OpenMP works great. We did a survey for MPI Plus X in 2015, and more than 50 of our NERSC users said the extra X is OpenMP. Next slide, please. So what is OpenMP? OpenMP is a industry standard API that works for C, C++, and Fortran, supports shared memory, vectorization, and heterogeneous device programming. The OpenMP Architecture Review Board, ARB, which many of our industry vendors, compilers, implementers, and government labs at media are team members. And Oscar and I are also on this committee. This committee released this OpenMP specification that compiler vendors would make it available so we all could use it to standardize the language parallelization, which is productive, portable, and with good performance. There's a good resources page, www.openmp.org. You can find specifications, download reference guides, examples, and the tutorials, and also information on the current compilers and tools availability of OpenMP specification level. Next slide, please. Over the years, OpenMP is 21 years old. Last year was 20th anniversary. 2 years ago now, 1997. And over the years, more and more features were introduced. 3.0 introduced tasking, 4.0 introduced SIMD and GPU support. 5.0 have more, even more support that's not available most yet. You're gonna see the slide what's introduced in OpenMP 5.0 in many areas. There are a few books along the way. Original one is Barbara et al. 2010, covers OpenMP 2.5. The second book is more about parallelism, algorithm, programming. And in 2017, there's a new book covers OpenMP features beyond OpenMP. Actually, it covers up to 4.5, released in 2017. There's also an upcoming book on OpenMP Common Core. So combined with other book covers more extensive knowledge of OpenMP. You can start with the Common Core to be released in November timeframe, and I'm proud to be one of the co-authors of that book. Next slide, please. The OpenMP compiler is available on laptop. Next slide, I'm not going to go through the details how you can install it. If without accessing to a, say, HPC computer, you want to play it on your own laptop, you can do so. Next slide is also Linux laptop. This one is Mac OS and Windows. Next. Again, next, please. So I mentioned exercises will be available, published on the Petascale Computing Institute website. And there's also, we are putting to the NERSC Query machine and NSA Blue Waters. You can do both of the CPU exercise on both machines, and for the GPU exercise, do it on the Blue Waters on XK node. There are instructions there. So there's some, basically the solutions out there already, but please stop and work on your own first before looking at the solutions. Next slide, please. How does OpenMP work? So it would, a para region would create a team of threads, and the work is divided among the threads so that they could run on different cores. And the thread would collaborate by sharing variables. There's also synchronization needed to make sure there's ordered accesses and to not corrupting your data by writing at the same time. There's, most of these synchronizations are done by implicit. So it's easier for the programmers to work with this programming model. There's also structured programming, means that you are getting to and out of the para region with a structured code. Do not randomly jump into a para region or get out of the region. The few components of the OpenMP that you need to work with is the compiler directives and clauses, that, and then the runtime libraries and environment variables. Next, please. I'll cut into those in more details later. So again, click this. So this is the hardware layer. Hardware layer, you have CPU cores and shared memory with SIMD units, vectorization, and GPU cores. On top of that is system layer around this OpenMP runtime library that actually also the compiler members would need to work with. And the OS support. So the users, the programmers, needs to worry about the layer in the program layer, which is directives, compilers, libraries, and environment variables that you would add into your code and use it during runtime. On top of that is the users, how to access the OpenMP. Next slide. OpenMP, you have a source code, and then you have compilers. So it's good that it allows you to keep a single source code for either sequential execution or parallel execution. Usually there's a special compiler flag you would add to enable that the compiler directives to be recognized so that you run it in a parallel environment. Otherwise, without the compiler flag, basically you would run your program and see it in sequential. Programming model is called a fork and join parallelism. In the sequential region, you have you still already have a thread, and at one time your program needs, I would like to have more threads to work with my code. Then you would fork a team of threads, and after that you could still go back to in a sequential region. The master threads will go on, and the next point you may create another parallel region. You could use a different number of different number of threads at that time. And also, can you click on this one again, please? It's also on the next region. Yeah, one more. So one more, please. Yeah, so I want to talk about the next parallel region. Is that it allows you to have one of the threads in the team to create nested regions, so that you can have two levels of parallel. And that thread becomes the master thread of that nested region.
But I can speak to the computer so that they can hear you.
Sorry. Yeah. Okay. I'm closer. I'll be closer. So next slide, please. For the memory model, basically all the threads would have access to a global shared memory, and each thread would also have a local private memory that have their own shared private variables there. Those private variables are only accessible to each thread, not to other threads, and threads would write to the shared memory to their shared variables. That's how they exchange it. But how the data transfer happens is transparent to the users. All you do is just write to the shared variables. And also synchronization is also implicit, as I've mentioned. I'll tell you later, and a couple slides later, where does those synchronizations happen. Next slide, please. So sequential code and OpenMP code like differ by a few lines of extra lines. Usually you can see you include an OpenMP include file and Praga OMP. In this example, just a parallel loop here. But there are also other directives you can use. So this is an example is about loops, but also again, OpenMP is not just about loops, offers a lot more. So next slide, please. Advantages, single source code, simple programming model, lots of things are handled by directives, not by the users like explicit message passing or something. All that you've done is implicit. And you can also actually increment your code, parallelizing it progressively. You can find a huge computation intensive place and add on OpenMP and work on it. And it's also portable with multiple compiler support. Next slide, please. Syntax, use OMP-lib or include OMP-lib, similar to C and Fortran. And then there's also Centennial directives, the different format, $, pound, OMP, usually for Fortran, and Pragma OMP, usually for C and C++. Next slide, please. These are just a list of compiler directives, not captures all, and it includes parallel construct, role sharing, synchronization, tasking, assembly, device. I'm not going to, we have a few slides on each, some of those, not all of them, more details. What does they mean? What do they mean? And then next slide, just to give you the components of that, of OpenMP. So next slide is on the runtime, the clauses. So you can also add onto the directives with the clauses, but like where you want a variable to be shared or private, different scoping and what operations you want, different schedules. Again, lots of those clauses as well. Next slide, please. The runtime libraries that you can inquiry how many threads I have, how many total threads, what my thread ID is, whether I'm in a parallel region, etc. A lot more as well. And then last is the next slide, please, is the environment variables. So those are, users can do it at runtime and without code. Set those and then change the default behaviors. Next slide. Next one, please. This is just showing you a simple program. Again, I'm showing you different colors of what you added to OpenMP. And at runtime, just want to emphasize that threads can run simultaneously with no specific order. So if you want hello world print, you can see different orders at different, and if you run it multiple times. Next slide, please. The nested OpenMP already mentioned is basically you can OMP parallel, and then underneath that another OpenMP parallel. So different compilers you would have to enable, like for example, OMP nested to true to enable it, and set a few other maximum active levels, etc. But other than that, nested OpenMP works. Next slide, please. Now let's talk about a few of the constructs. The biggest one is a parallel construct. This is the only way that you can create a team of threads. And then with that parallel construct, you have this for C, there's a blocked structure, so you have curly braces. If it's only one line, the curly braces can be augmented. For Fortran, you have to have parallel and OMP and parallel. And within it, all the threads will execute the same code in it. In this example, different thread will work on, if I'm different ID, I work on my function on it. Sometimes you have the work sharing loop, then each thread would get a segmentation section of the loop to work with. But overall, inside parallel, you have multiple threads and each thread will work simultaneously. And at the end, everybody has to wait at the end of the parallel to go on maybe another parallel region, maybe a sequential region, but everybody meets there and then go on. Next slide, please. There's clauses you can add, if or num thread. You can see how many threads I want for this parallel region, and also if if my region is too small, I don't want a parallel region. So these things you can add. Next slide, please. So I just want to show you different ways of set number of threads for my program. If you don't create this implementation, we'll have it. didn't say what you get. That's what you want, you would request for. And before I say that, actually, you would, whatever you request, you always have to check how many you get. Implementation may get you fewer than you requested, depending on their constraints on OS or available course, etc. Always check. But other than that, before you check, I'm talking about ways you can request and how the compilers will recognize or to choose which one. There's a precedence there. When one is over 2, over 3, over 4. So I talked about the 4. 4 is you do nothing, you get compiler default. 3 is you say your runtime export all num threads equals something. And 2 is if you actually have API say OMP set num thread something in your code, then you do export OMP num thread. It won't change that. It'll abide by your API setting. API setting works for all the following parallel regions if you don't change it. And the number 1 is for each parallel region, you can set the number of threads explicitly. It won't affect the next the next region. I'll go back to 2 or 3 or 4 settings. Next slide, please. So OpenMP has a relaxed consistency memory model. It means that it allows you to have a variable have different values, whether it's in the cache or in the main memory. The idea behind that is every time you have to make sure everything is consistent. For example, processor 1 change something in cache 1, and if processor 2 wants a thread 2 or wants to use it, if everything's consistent, then if the data has to be made into shared memory and process thread to get it back, then it becomes completely sequential. So with this relaxed consistency, it allows you to work simultaneously. Next slide, please. Synchronization. So at certain points, there are ways to do higher level synchronizations, including critical, barrier, typoing barrier, atomic, ordered. I'm going to talk about critical and barrier and where are these implied. So next slide, please. Synchronization allows you to have ordered access and make sure data are consistent. So here one is the barrier. Barrier means I want to make sure every thread coming to this point before I go on with next region. So on the right side of C++ example, say you have a first region, have some inside parallel region, you have some work done, and then you want a barrier there so that the next work B, if needs results from A, you would make sure everything for A is up to date. On the left side of the function with a more detailed example here is first loop AI, calculate AI. And then I can do something else that I don't need A. But then at this point, actually, I introduced a new thing called known weight. I'll have a known weight slide later again. So when you're updating A, it's okay. I can go on to do some other computation but do not need array A. But then I noticed that for my second do loop, I will use A. I want a barrier there. An explicit barrier. If I don't have anything in between, then with OMP parallel do, it will already have an implicit barrier for you. You don't need that. But if without it, you did something else and then come back to before your second region, you want a barrier. So next slide, please. The critical, again, we try to make sure sometimes when you update a value, x equals x plus 1, if every thread does that, it may have a data race, whoever actually wins. Because actually, you want this to, sometimes you would add a value to, you want each thread to do it one at a time, so access each one instead of some threads because they're faster and use the other value. Like example, if you want to deposit money, you want to deposit 2 amounts, and then you don't want just one go through. So that's a critical session will help you with. Make sure it's one at a time. You can name a critical session. Without a name, all the critical session in the region, in the whole program can be done one at a time. The names and only the names are the like a little subgroup of critical sections. Make sure those are one at a time. Next slide, please. Flush, I just want to, here I mentioned. So at entry and exit of parallel regions and entry exit of critical regions or an implicit and explicit barriers, things are flushed. If you do your own flush, you would say, I want flush this variable, that variable takes, it's hard to do, you may miss something. But those implicit barriers are done for you. You don't have to worry about it. After that, your data is consistent at this point. Otherwise, if you write to it at the same time, it's called a condition called data race. Data race is the hardest problem to debug in OpenMP. Next slide, please. Master and single. So master, basically, you just say master thread is thread number 0, is a master thread. You say only my master thread is going to work on this piece. You can say OMP master. And OMP single is whoever goes there first can do it, but just only one thread will do it. So OMP single. The difference is a master thread, there's no barrier at the end of master. So masters do that, all other threads will already go on. For single, even though only one thread is working on it, all the threads have to wait for it to finish, to go on. Next slide, please. So thread of safety, mentioned about this critical critical atomic barrier, etc. But in general, there are other things like OS functionalities, I/O. Sometimes the libraries are not thread safe. So try to check to find out if they are thread safe. If not, do it. If you have to do it serialized by just one thread. Next slide, please. Here's an example, doing calculation on pi. And then at one point, each in a little thread section, loop section, each thread has its partial sum. And then you want to add to your overall pi, but you do it around the same time, you get the data race. So this is a pi OMP wrong, not C. Next slide. So how to avoid that? One way to avoid that is that each thread would have you can have an array, that each thread would have an array component, array index, that it's my sum. Then you add together all the values in the array to get the overall data. This is correct. It gets you correct results, no more data racing, but look at the performance. Running with 1, 2, 3, 4, not getting you too much performance speed up. So the reason of that is called something called force sharing. Force sharing is a common symptom that you would see in OpenMP. So next slide, please. So how did force sharing happen? Is that you have a sum array 0, 1, 2, 3, but if they are small and they may be on the same cache. So say, for example, hardware thread working update sum 0, but then simultaneously the thread 2 wants to update sum 2, but they're on the same cache value. So after the thread 0 updates sum 0, thread 2 knows that my cache line is now outdated. And I have to actually grab an updated cache line before I can update sum 2. Then after I did sum 2 and come back, thread 1 wants to update sum 3. And hey, I have to wait for thread 2 to finish and then go back to main memory to update my cache line. It's back and forth cache line updating to the main memory to get the data. Got to basically serialize your multi-threading, updating your sum array. That's called cache line, the force sharing. The next slide, please. So how do I avoid force sharing? I would make sure all my sum 0 and my sum 1 is on different cache line. So if I pad it, give me the additional dimension that make sure it's, I know my cache line, cache size of this computer, so I pad it big enough. Yeah. So yes, they're on a different cache line now. Even though it's still an array, my performance here with the padded, you can see much better. This kind of adding a pad is kind of awkward, and we have also its implementation dependent. If you're working on different platform, you may change the pad size. And next programmer comes in would say, what did you do the previous program? Why are you doing this? It's all hard to understand. So it's not a good way to do padding. It's not natural. But it explains the concept of force sharing and how to avoid it. So next slide, please. So let's use critical. We know that the data racing to update it one at a time. Now we can go back to the scale instead of array. Summation, and then within each for each thread, the sum originally is as private, but then you add to pi one at a time, and you would get correct results. And also the performance I'll show at the end of all the high examples. It's as comparable to the padded array. So next slide, please. Now let's talk about the loop-based parallel OpenMP, and it's called single programming multiple data, SPMD way. So again, as I said, in parallel regions, threads would share work. The first way with the loop is that I just say OMP parallel do, that's for the Fortran, and then I have a do loop here, and thread would divide work. But another way is on the right side. So I don't think this should do there. There's no loop there, but then each thread, I know my loop index. I would figure out my start and end index, and then there's a do I equals start end. I do my little section. So some of the programs actually prefer the right side way because it's more their own, have better control. It would sometimes help you to do help you to get more compile optimizations. As cache misses, if you're viewers, you want to deal with that. Next slide, please. So this basically, again, tells you the syntax of the work sharing loop. And there's also introduced clauses for schedule. You can have different schedules, and it will be divided. And I have another slide to tell you different schedules and how that works to divide work in the loop. So this is the core, kind of hardcore of OpenMP, one of the hardcores besides tasking, the parallel loops, work sharing loops. Next slide, please. The loop index is already made by default, as default for you, because you don't want that different threads have have the shared loop index. But if the next level index, you have to make sure to declare it as private by yourself. So schedule I mentioned, when you're doing the parallel for loops, you have different ways. Static is you just divide it by number of by different chunks, and each chunk has the number of chunks in there. If you don't say chunks, it divides by pieces of how many threads you have. So it's predetermined, and compile time determine which threads will work on. So it's good. But the disadvantage with that is sometimes each thread, the work assigned to them are not even, or even the loop number of loops is not even, or each loop the work amount is not even. So you have to it would get you more loading balance with static. A good compromise is not do stat without a chunk, do a moderate size of chunk, so that loop balance will be. Dynamic is also divided into chunks, but then each thread, you can do the first chunk and finish and go back. So whoever works faster will get more work done. It helps with the total load balance. Guided is similar. I'm not going to detail of those. We can skip that slide. Go to the next slide. Just mostly used are dynamic and schedule and static. So here is working with loops. What you do when you add OpenMP, you find a loop, computational intensive loop. And then you have to say, if I want to divide work, I have to make sure they are not loop dependent they are not loop carrying dependencies, meaning my next loop index work depends on results from the first index. That way you cannot parallelize it. So for this example, you could work on J here is J equals +2, like the loop index. Here you would say J equals +2, you have to, for each I coming in, next I coming in, and my J is not known yet. But here you say, actually, I know that J equals 5 + 2 times I + 1. Now it's independent. Now you can actually parallelize it. Now the loop carry dependence has been removed. With that, and you add OMP parallel 4, you parallelize it. Next slide, please. The no wait I already mentioned that if it goes with OMP4 up there at the end. The second OMP4, if you don't have a no wait there, when you are done with the loop, you have to wait at the implicit barrier before the big AID equals big calculation 4 can be carried out. But if you know and the calculation doesn't need B or C that calculate, and ahead of that, you can say, and thread whoever finished that OMP4 can go on with the next loop, next part of the code. Ordered and collapse. Ordered means when you do parallelization, you actually still make sure the loop is carried out as if it's in a serial order, sequential order. Collapse means if you have multiple layers of do loops, you can collapse them into one big loop. Then when you do work, schedule or anything, you treat it as an internal, just one big loop. It helps you to sometimes if you do only decompose the outer loop, like sometimes there's like the outer loop in length is really small, so each thread doesn't get enough work. So you add it, make collapse 2, then you have a bigger loop to work with to distribute to the thread team. You could another thing is without collapse, you could sometimes consider swap the loop order in so that outer loop. If you only not parallelize the outer loop is big enough for you to parallelize with. Next slide, please. Here, basically, you have seen OMP parallel, and then the next line said OMP parallel do, OMP do. Just for your convenience, we could say OMP parallel do in one line. It's exactly the equivalent of 2 different lines, just for syntax, for easy. So it's called combined parallel work sharing constructs, the C and Fortran. And then there's also sections in both C and Fortran. And in Fortran, there's also something called work share. Each different code works by worked on by a different thread. But again, this is concept of combine parallel and an OMP something else. Same syntax, same meaning. Next slide, please. So reduction is a very useful concept that is used in OpenMP. So in serial code, sometimes you have on the left side, what you have is a very big looping dependency in the serial code, but what you're doing is trying to accumulate. Say you want to accumulate A of I to one big value. That's that average. You cannot just easily divide the loops into sections because they have dependencies. But with the production implementation, everything is just handled by OpenMP without you worry about it. It did this way that each loop section would have a private local accumulation value. In this example, it's average value. So you have everyone has local average to add them together, and then at the end, the implementation will do a global reduction, which means they add these values together. It could be different algorithms that you don't need to care about. It could be so you have like say 10 threads and you have 10 local variables. The OpenMP implementation will gather them and reduced to the last one. There are already defined arithmetic plus and minus times multiplication, max, min, etc. And then it would choose a local initialized value for each local private variable. Or if the sum, the initialized value will be 0. And if it's 1, if it's a multiplication, and the initialization value will be 1. So that makes sense when you add them together. Next slide, please. In OpenMP, users can define your own reduction operators. You have to define a name, a type, what function you work with. This operator will be, and then you can declare it, and then later on use it in your own application. Next slide, please. I'm not going into details. That is to say, telling you this feature is available, so you can explore if the available operators are not enough for your application. So here, PI was reduction. The reduction is inside the parallel region, but then the reduction is also done by the global implementation of the adding together all the private sums. Next slide, please. There's only reduction is very simple, only 2 lines. There's also a type of algorithm that it's like away from pushing. So you have to calculate every single, it is on a grid, every single grid from the corner that in order. And then next set of data is, for example, in Bij equals something of Bi minus 1j plus Bij minus 1. So you have to wait until those are available for you to go on to calculate Bij. So this type of thing is called do across. OpenMP had made do across type of algorithm work very nicely. So you would define something called depend as a sink, as dependency as a sink. Sink means I have to wait for this to be ready before go on with my next one. And then there's also a source. So source means now it's Bij is ready for the next Bi plus 1j to use my Bij. Okay, next please. Okay, so the next topic, completely different topic, is the data environment. So as I mentioned, it's done by shared variables that you can exchange data with. So most data variables are shared by default, and then OMP, you could say a clause default shared. If you don't say it is shared, you could default private, default something else. But they are shared. But what are these shared things? So common blocks, for Fortran, the save variables, module variables, and for C++ is file scope variables, static variables, dynamic allocated variables. Basically, everything on heap is shared mostly. And so there's some other variables are private by default, like loop indexes are private by default, and stack variables. Another big thing you can utilize that if you define your own function as a routine and you declare some variables there, they're private by default. This is easy for your writing a code. If you have lots of variables and you have to declare private, putting them into a program saves you a lot of energy to have to spell them out on OMP directives to say this is private. Okay, next slide, please. Here's a data sharing example. So OMP Pragma Peril. Above that, you have double A, which is a global variable, and index is defined before the parallel region. They're both shared. In that work function on the right, there's a static variable count because it's static, so it's also shared. But then the double temp is defined inside the work function, so that's private. Here's just a diagram say which are private, which are static. And also the temp, after you go out of the parallel region, the temp is out of scope, but other A and index account are still in scope. Okay, next slide, please. So here, private. There's a concept of original variable, is that you go to a parallel region, you define a private variable, then the implementation is giving a private storage space to that private variable, local to that thread only. So you mask the original variable. But original variable is the one outside the parallel region that's already there. And then when you get out of the parallel region and all the private data, private variable will be out of scope. You go back to your original variable. In this example, you have int temp equals 0 as the original variable. Then you have a parallel for private. So inside the temp, and you say, I want to actually update to temp. This is wrong because this temp is not initialized. There's no data. It won't work. But anyhow, when you print temp at the end of after you exit parallel 4, that temp will be 0, which is the original value. Yeah. Okay, next slide, please. So as I mentioned, the stack private. So everything on the private, the private variable is owned by the thread. That thread is on that thread stack memory. There's a default stack size. Sometimes it's not big enough. And when you run it, you just run into, mostly you will see segmentation fault. The first thing you want to debug this is say, let me increase my stack size if it helps. Because usually it's too small. So you would set it and try to see if I could give it enough stack space for each thread to work with my private variables. Next slide, please. So default, I mentioned, if you don't say anything, default is shared. And if you want to say default private, you can, but then you have to then because everything shared by hand. But then another thing we want to emphasize, the default noun is your friend, because With it, now compiler will just to try to make sure you actually declare everything, either private or shared. Without it, I'll tell you, you forgot. So in this example, so for J equals the next level, and there's also a Y, if you don't say it, if you compile this code, compiler will tell you forgot these, which is helpful because J is very forgetful. You would say forgot to declare it as private. So this is a good programming practice. Just we want to recommend. Next slide, please. The first private helps you for the previous example of temp. So actually, when you get you have original variable, and then when you get into prior region, you want some variables to inherit the global the original variable's value. See, I want first private. Then I have my value when I get into the OpenMP region. So it basically initialize the values as compared to private. With private, you have the value is uninitialized when you enter the parallel region. Next slide, please. The thread private. So it's especially helpful for global, the module variables in or the global comment that used in Fortran. It works for C as well, but we want to just say it's especially helpful for the Fortran exam users. So what it does is, you define in the common blocks, and the common blocks is used by multiple program subroutines in different parallel regions. So the thread private makes sure that even though each variables are private to each thread, they are consistent when you enter into the next parallel region, as long as the number of threads are consistent. So the thread private data, you get on to the next region, you still have it. But then, and you can also copy in the variables from the master thread to each thread, so that saves you a lot of work to get the initial value of the common blocks. Next slide, please. A new topic, tasks. So with Opera for loops, if you know the loop count, you can divide the loops into different threads to work with. What if you have, say, a linked list travel? So you have something that you don't know how long is this? Can't do work sharing loops at all. So what task does is you would pack a block of code, a pack of the data that comes with the code, put into onto called task queue. And then the team of threads you already created would come to pick a task from this queue. And then when it finished, go on the next one, sort of dynamically finishing this task pool. So one big, so task sometimes can be when you pack it, you can be executed immediately or can be deferred later. There's also some kind of what we call task wait, or one would all the tasks that the creator has to finish. There's also rules I'm gonna talk about a little bit later. So the task, next slide, please. The left side is a serial code. It's a famous Fibonacci, the sort of hello world for tasking example. So you have, when it's small enough, you calculate directly. But then when it's bigger, you would say, I want to calculate n-1 of Fibonacci and -2 Fibonacci. Then how does n-1 is calculated? Is I would do actually n-2 plus n-3. So all these things, I just create queue tasks for each, and then a big queue in there of it all. Actually, when real execution, it has to go bottom up to finishing up. It's called a divide. You first divide first into 2, and then you go down, 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 and then you conquer toward bottom up. So divide and conquer algorithm. But the idea is that each of the calculation of Fibonacci is a task. And then you finish Fibonacci n-1 and -2, and you put an OMP wait, task wait. Task wait means finish the first 2 tasks, then I can return x plus y. But it's actually a recursive tasking and a big pool working with here. The concept here is task, and what does task wait mean? Task wait means wait for the child task created for the current task to finish. Okay, next slide, please. There's another example, it's also in the exercise, that try to figure out a way to print. Sometimes when you write it, sometimes it prints, I think car races is fun. Sometimes it prints, I think race cars are fun. So the idea is print car and race as tasks so that they can, because if they're tasks, there's no specific order which task we run first. And this is how it does. When you pack the tasks, the common practice is to have a single thread to pack all the threads. And this single thread, if they're figuring out the task pool is too full, sometimes it can help finish the task. Otherwise, all the other threads would come to work on these tasks. Next slide, please. Tasking the scoping for the data, it's pretty much similar to the original regular data scoping, except one thing is that if you declare something private to package your task with your data and your code, when you say private, we know actually you want it to initial values, everything to be available in that task because you don't know when the time the task is executed, data may be changed. So when you pack the task, it's a private, we made actually it to be first private for you, so you get the data with it in packaged for the task. So in this example, if this task and you say A is shared and you say private B, and when you compute A and B and C, we actually give you initialized value. So B is actually first private. Right, next slide, please. So this is an example for the serial code parallel linked list traversal. So with tasking, it's very simple. You just say first private P, and then you process P, and then P equals next P. Come back when it's next P, that process next P is also a task in the queue, task queue. If you're not doing it with tasking, you have to do three steps. First, figure out, just traverse the whole linked list first, find out how long is this. Second, make it the pointers, data, everything into package into some kind sort of data structure such as an array. And this last step, you would actually, based on the number of the loop counts now, we actually now decompose the array. Instead of this three-step compound method, the linked list with the tasking is much more elegant. Okay, next slide, please. So here's a PI with tasks. It's very similar to Fibonacci. You would decompose it. And PI, you had a start and end, actually divide it to half and do the other half, the half, divide, conquer. So I'm just putting it there and don't look at it in detail until you try to work on it first. This is also part of the exercises with all different ways of writing the Pi program. Next slide, please. This is basically performance results with different ways of original way, and then another array, and padded, and critical, and loop with reduction, and tasks. So as a quick summary is with just array, it may give you fast sharing, so first speed up. When you pad it, they're on the different cache lines, and performance is good, but implementation is awkward. Critical is easy and useful. Loop as well. Loop with reduction is as easy as well, but loop add a little bit more overhead than just with the SPMD without the loop in it. And tasking for this example on the Apple machine, it performs surprisingly well. When I try to reproduce it on the HPC computers, I don't see that. It's actually worse than the loop and reduction and critical. So next slide, please. So I mentioned about task weight. There's also another concept, task group, which is introduced in OpenMP 4.0. Allows you to weight. You have a group of tasks. Allows you to weight not only your direct child, but also the descendant child of your direct child. So you have a good weight point. Wait for everything to finish. You can use the task group. Next slide, please. There's dependencies you can use to help you with task synchronization. You say task, and on the left side, example is if there's actually there's for the red one there's the typo there, private OMP task wait. The last line should be. That means before you start the red task, you have to wait for green and blue to finish because there's a task wait there. On the right side, if you say dependency, if I say my red is only needed for the for the blue task to finish. I do not have to wait for green because I only wait for when I red one. I only in and out of X. I need in X. In X means I need X to be ready for me to start. But there's no need for me to finish another task that I don't need. I only need X. As long as X is finished, which is the first blue task is finished, I can start my red task. Just adding this dependency, telling them which I need as dependency, in or out. That's helpful. The next slide, please. The task loop. Task loop is like basically working from a regular loop. But when you cut them into pieces, you treat each one of them as a task instead of, it's similar to dynamic. The dynamic is actually still executed in order of the loop. Once you have the chunks, one each come back to work on sections. The task loop, you basically turn into each of the loop decomposition into each individual task, and they can be more dynamic. They can be executing in any order, helps you with dynamic load balance. The next slide tells you more about how task loop is good. There's another class called, next slide please, called grain size. So when you decompose the loop into different pieces, now you give a size for each piece. And this is the equivalent of if you do a manual optimization called blocking maximum, you would get out when you do the parallelization, one block at a time to help you increase the cache realization. Now you don't have to do manually. With a task loop and grain size, that's the equivalent of the array blocking for you. Okay, next slide, please. Okay, the last topic I want to cover is the thread affinity and data locality. Affinity basically process affinity. You bind your processes such as MPI tasks to CPUs. Thread affinity is now you have threads that works under that process. Could be MPI process, could be OS process. The threads you want the CPUs that are allocated to their process. You want your memory that thread works on to be close to where the data is. You want your do operations, you want work on those memory, you want memory to be local to your CPU. You want cache locality means you want reuse cache as much as possible. So these are the basis for correct performance. Otherwise, it's also easy, sort of easy low-hanging fruit. If you don't do it right, you get very big penalty in performance. You want to make sure you get this correct. It's sort of advanced topics, but actually it's used in practical running HPC programming and running your applications. Next slide, please. So a quick Intel Haswell on the Coarse system. You have basically under the concept is that we have two sockets. Each socket has how many cores. Each core has how many hyperthreads, and for each socket, it has memory attached to it. So the cores on the remote socket has further memory access to the memory that attached to the other socket. So, and there's a NUMA CTL-hack hardware tells you the details of that. We usually, if you're getting onto new systems, always figure out how those for these processes. Each process has how many sockets there are, how many cores right there, and then next slide, please. One quick thing is that you usually do not want to use more threads than a NUMA domain has, so that all your threads will be within the same team that works in the memory located in that NUMA domain. If you have more threads, then some of the threads will have to work on the memory at the other NUMA domain, which is farther. When it's farther, you get all sorts of memory penalty, access penalty. There's a ways to do a thread affinity. You can define places. Each thread can be a place, a core can be placed, means all the cores within that, all the threads, all CPUs within that cores can be allocated for the OMP threads to work on. There's also bind. How do you bind your thread core CPUs with the places? How do you bind it? Next slide will show you there's options close, thread, and master. So when you see the diagram, it helps you to understand better. Next slide, please. So here, without binding, it's nothing. But here, if I have 4 cores and each core has 2 hyperthreads, If I bind to close, means if with 4 threads, it'll use 2 threads each on 2 cores. It'll idle the other 2. If I want spread, it means I will use 1 thread per core, which is better balanced and use more memory. Master means you bind it to the same. Sometimes a master binds to the whole socket, and then your other threads will bind to the socket as well. Okay, next slide, please. Some of this exercise with these, you can just see the numbers and find out with the still changing of those variables, how does my binding differently. So there's another topic is about first touch memory. So when you decompose at OMP power 4, we work on these variables. AI, AJ equals BJ plus D, all these variables, without initializing them correctly, also with the same parallel form region, the data actually is called first touch. If you initialize your data with only 1 thread, everything will be local to that thread. So when you create a parallel region, all your other threads will have to work the memory closer to thread 0, which is mostly far from your local threads. So the penalty, you see that is with and without first touch. I think without first touch, they're the same all the way up to the first socket, 32 threads on 1 socket. Then from 32 to 64, you do first touch correctly, you get the blue speed up. Not they're all tight because everything on this core socket, you're having access to the other socket. Cause your performance slow down. So the first touch is useful. You try to do it either same initialization, because the memory is set at the initialization time, not at allocation time. Or you try to say, I never use more than 32 threads on my this core, this node, because I know the 32 threads is how much 1 thread is. Next slide, please. I mean, one socket is 32, so if I don't use more than 32, I'm good. And the proc bind choices, the thread I showed, the close and spread. With the close choice, with that small example, you see half of the cores are idle. So here again, on the Haswell node, if I use spread, this is for the stream memory bandwidth. If I use close, I'm wasting the other half of memory bandwidth. So that's the blue, the higher the better here, the bandwidth. So the spread gives you much more performance. Next slide, please. Here's a quick example of showing if you don't do the good affinity, the naive one, for one of the applications, you get 33 times slowdown without correctness. So this is useful. Different compilers have something to give you to show your affinity. So we have added in OpenMP 5 environmental variables, OMP display affinity. If you turn it on, you get a good debugging data, whether your application is giving you the right affinity. And you can also play with your own format, however you like it. Next slide, please. So say if I have a code, serial code, what should I do? I want to add OpenMP. What users have to do is users have to be responsible to decide where should I add OpenMP, what my algorithms are. Then the directives, just follow your algorithm. So you need to make sure these are the intensive, computation intensive locations I want. So you should do some profiling to find where is the hosting area. And the algorithm sometimes is easy. Sometimes you say, I want to change, I want to use tasking. It's not easy. So rewrite. Say, I want to just OMP parallel directives. It's easy. But also you have to make sure which data should be shared, which data should be private. Whether I can, no wait, because I know that following data doesn't use it. So the performance-wise, and it's not, say, add OMP parallel 4 and my work job is done. It's not that. You can explore a lot of things in OpenMP to improve your performance. Next slide, please. This is also a concern of fine grain versus coarse grain models. Fine grain is that you do OMP parallel one at a time, and you have sequential codes in between. The coarse grain means I have big parallel region, and everything in between is just my do loops. So everything in between is parallel. So there's pros and cons. The left side fine grain is easier to do, but also you have the sequential code bottleneck. You also have, because you're creating and destroying threads one at a time, each one after another. Although some implementations would say, even your user says destroying, they may not be destroyed for real, but then still there's overhead of managing. On the right side, it's harder to program, especially if you have sequential code to deal with that, but it's also low overhead. And you can try with either. Next slide, please. This is one a real application, Jacobi code, and ran it, and we see it's good. Has some speed up, but not perfect speed up. Trying to think of why it is this case. Whether I, have load balancing issues, whether I should do different scheduling, whether I'm getting the good affinity, whether I'm having too much synchronization overhead, whether if I have my application is too small that I don't have enough work for each thread. So this is also an example. You can try to do different things for your code. Next slide, please. I just listed a few of best practices, the OpenMP. So when you add OpenMP incrementally, don't do it all at a time, or all of these at one time. Do one loop or something and check your correctness. If you do too much, come back to find debugging, it will be really hard. Also, try to minimize sequential area, because if you have, say, 10% of code is sequential, however many threads, how many processes you use, it's like your maximum speed up is 10x, right? That's Amdahl's law. And test with coarse grain parallelism. Also, reduce parallel regions is good for you to reduce overhead. Shared variables, critical barrier, everything is very costly, so try to minimize if you can. If you can do no wait, do that. And there's sometimes you can do loop collapse, loop fusion means exchange loops, and loop permutations, loop change, all this blocking you can do. Load balancing, try different schedules. It's actually schedules as easy, also low hanging fruit. You can try it at one time. OMP set, export OMP schedule equals dynamic something, static a chunk. Static with small chunk is a good thing to start with, because it's quicker, and it's also as everything is determined at the schedule time, at the compile time, so it saves runtime overhead. SIMD for vectorization, and look out for false sharing. Beware of NUMA domains. Don't use more threads than you have on NUMA domain. If it's pure OpenMP, you would use that. But then you have to make sure you do the correct initialization. I think this is all I have for the first part. You're welcome to ask any questions on the Slack channel. I'll just go on with the Oscar's presentation next. Thank you. For the sake of time, I don't think we should answer questions now. Or we could do, if we do have time at the end, we could do it together. Otherwise, do the Slack channel, please.
Are there questions from any sites? Should we switch to Oscar now? Helen?
Yeah, pass out to Oscar, please. Oscar, are you going to present from your WebEx directly?
Are you ready, Oscar? Okay, we have a few questions for you, Helen. What are the differences between clauses and directives in OpenMP?
Clauses are the modifiers to directives.
Did you hear me, Helen?
Yeah, I answered. Did you hear?
You were get near the microphone, please, and answer
Clauses
again.
are modifiers to the directives. For example, you have OMP parallel directive, and then you would say, I have some shared variables, I have some private variables, I have number of threads. The other three are clauses. But OMP parallel, we could call it a construct. It comes with the execute the codes that you defined to work with the OMP parallel region.
Can you elaborate on the explanation of what false sharing is?
False sharing?
False sharing.
Yes, so if multiple threads working on some variables that they share the same cache, so when one thread update that cache will be invalid. So the next thread, even though it wants to update another variable on that cache, it has to get the fresh cache first. That getting the thread has to invalidate the cache he owns, this thread owns, and getting a new copy. So invalidate the cache and get a new copy, update my variable in this cache line. And then the next thread yet to update another variable in that same cache line has to invalidate his cache line again, getting a fresh copy. So the back and forth of getting invalid the cache line and getting new fresh cache line is how it slows down the performance. This is called false sharing.
I think someone answered it, but so false sharing is similar to cache invalidation?
The cache invalidation, because some threads already update the cache line you have to work with. It's related to cache sharing, or the same cache line that multiple threads to work with.
And so it leads to unneeded reads and writes, is that correct?
What do you mean by unneeded read and write? Oh, yeah, you could say that, yeah. I need to get a new copy of the data, which is it's a read. And when I write to it, I make sure I'm writing to the most up-to-date variable, that if somebody already updated it, I cannot write to it.
How do you know CPU to memory organization, and how can I know how many CPUs are sharing one cache?
So it depends on which, by CPU, do you mean by threads? Here? So the threads I work on and depend on what variable I'm working on and whether this variable is on the same cache line as another variable is working on. It really depends on runtime, which threads are working on which variable. So for the array components, they are most likely to be on the same cache line. The next array component like AI or AI plus 1, plus 2, they most likely are on the same cache line. But if I pad it AI 0 and AI plus 1, 0, they could be on a different cache line already.
Are there other questions?
Is Oscar out there?
Probably not going to be able to hear you on that.
Switch.
Let me grab it.
In OpenMP, can you control the use or no use of hyperthreading?
Using so you can decide whether to use it. Sometimes some of the job launcher has a flag to say how many threads, hyperthreads per core. Sometimes you would do it without that specific flag. There's a way to decide how many CPUs I give to each process, and then so say you have 16 CPUs for that process, and then if I say I want 8 threads only, then if I do close, I would use the 4. By doing OMP proc bind equals close or spread, with the number of threads you have, with the number of CPUs you have, you can control implicitly whether you're using the hyperthreads or not. Depends on the launchers how you control these things, and on plus the help with the OMP environment variable settings.
On slide 43, does do ordered force sequential execution of a loop that's embedded in some parallel region? If so, why wouldn't single suffice?
43 is ordered, right?
Do ordered.
Do ordered, yeah. You mean why it's not equivalent of the sequential?
Why wouldn't single suffice?
Oh, single. Single is actually the same as you saying I'm doing it sequentially. Good question. Then in the next slide, I think I mentioned about the collapse for the dual cross. If you look at that, there's details about actually slide 48. You would collapse them, you order them with the sink and source. So it gives you the same sequential order, but it's somehow still done in parallel.
I think there's one
Otherwise,
more.
if you say with the order, I'm never getting anything parallel there.
Should be on there.
I don't know where the audio is not working.
I think there's one more question. Do we need to be concerned about code transferability between different node CPU architectures when using data locality routines?
Should be on.
So depending on what data locality routines you mean by the cache.
Trying to get
The WebEx.
Your audio's breaking up.
Yeah, I think you would have to worry about these
You
things.
have the email.
It depends on you. The source code might be portable, but the runtime tuning, how many cores, how many threads you run, things and size, whether you want to do some loop blocking or other things are the ways to tune your cache utilization or helping with the data locality. So yeah, it may seem that source code everything is portable and you do not need to change, but the runtime you have to optimize it.